All right, so right here, obsolete, delete, obsolete. We're already pointing to the last one here. So this one gets deleted. And so this is deleted. We're no longer going to use the obsolete. It's created inside the loop anyway only. And then we continue our iteration, and it says, as long as iterator is not null. But obviously our iterator, temporary pointer, which we used to point to one object, another, finally is null. So we reach the end of it, and we just exit out of the loop. We get out. So this does remove everything that was allocated dynamically except the root, because we leave the root alone because we say, root, what are you pointing to? And that's the pointer to the next node. All right, so after that, this demo here also suggests that, well, you know what, just to make sure that nothing looks strange anymore, we should also point our root next. Basically, make sure it's pointing to nothing, because we just deleted everything. If there was some prior to this, if there was something created new and we were pointing to something real, now let's just make sure that we point to none. So let's make sure that we print this list, right? After dynamically populating it, let's actually call print list twice, before and after, right? So once we insert a couple of nodes, we say print. Then after we remove them, we will say print list again. Why don't we do that? So build and run it. And so there you go. So those two first they show up, then they're gone, right? They're deleted. So we can, this demonstrates that we can organize the list in such way that we give a root node special treatment. Say, use it to control the list. Don't even use to store data. This is our access to that chain of dynamically allocated and deallocated objects, right? So there's this possibility. So keep this list highly dynamic, allocate everything by new, store everything in the list beyond the root node allocated dynamically. Then we can assume, then we can make this assumption like we did here, that only the root node is allocated inside as a local object. We don't have to delete it. It's our local object. However, when we create new nodes, they will be allocated in the free store outside of this main function. Okay, so with that in mind, with this demonstration in mind, moving on. So it says, let's write the new version of the stack, version 3. And let's support the following interface. So why don't we just do what this thing trying to asking us to do? Demo project, right click, new text document. We'll say stack, whatever, stack.h. This is a header file. And just open it and simply copy and paste, because this is supposed to be our interface. Control C, and that's the new version of the stack. All right, so it contains, let me actually move it to the next tab group here so that you have better view. All right, so push, pop, top, two versions of top here, size, and is empty. Okay, so that should look familiar. And so the idea is this, as this homework assignment suggests, that apparently what I'm going to do is include, apparently it would be appropriate to do this. Include node in the stack object, right? And then include the stack.h in the main file, right? So implementation file includes stack.h, stack.h includes node.h. How about that? And again, it sort of like really bothers me that we never specified the header guards. We should. So if not defined, something like node h included, then define it, and then at the end simply say if and if and do that. All right, so now we have the header guards here, and again, node should also get the same header guards, but we never define them, so that's not good. Now, so far I don't even have a constructor in this class. It's probably not the right thing to do, but we'll talk about that in a few minutes. But the idea is to say, to demonstrate this, is that we create a stack, right? Stack st, we create it, and then we can say st dot push, push a value and integer value. I don't know, 1, 2, 3, 4, 5, right? Push an integer value on the stack. And the rest of the functions, push, pop, you know, simple interface. Class stack can now delegate the work to class node. Push can be accomplished by insert. Pop can be accomplished by remove next. And top can refer to the data. And size is the same as the size of the list. And is empty is simply checking the size if it's 0. How about that? To demonstrate, what we need to do here is that we should add a node, I don't know, mroot at the top of the stack. So now we have the root object of class node that we already know how it behaves, right? So then if someone says push, and again I'll cheat a little bit and just write this in line. So in this case, push can delegate this work to the root node and say, why don't you insert the new node, right? The new node, and populate it with this value. So let's resize this. And you get the idea. Mission accomplished, right? This will work. The root will insert brand new node, take the value that will contain 1, 2, 3, 4, 5, and we're building this chain of objects. So the stack is just an adapter, the wrapper around the node, and behaves like a stack, but in reality is using what node already can do. It can insert, so a pop here can potentially do something like this, right? Simply, as it says, mroot, remove next, right? We will assume. Now, I think we're operating under assumption here, the way I feel this, is that, let's start from scratch here. So now we have, actually let's save this and start from scratch.